Hey there, and welcome back to ECE 382. We're still in Module 3. This is part 2 of the video. Today we're going to be looking at the architecture of our system, which includes the Cortex M processor. So taking a look at the processor, what does ARM stand for? ARM is the Advanced RISC Machine Processor. So this is similar to RISC versus CISC kind of idea, and the MIPS processor we use in 281 was a RISC machine, and we'll look at that again, what that means, but remember that's the reduced instruction set. And we use ARM in this course instead of MIPS because ARM is a little bit more advanced than than MIPS. It provides a lot more capability, a lot more, while it's still a reduced instruction set, it provides a lot more instructions than MIPS. And ARM is pretty prolific in the industry. So Raspberry Pi uses ARM. More and more, one of the new Microsoft Surface Pros uses ARM. And so ARM is everywhere, Internet of Things, wearables. And so understanding how the architecture works, understanding how ARM assembly works, really help you have a great idea of how the industry of embedded systems works and give you that background. So looking at the architecture of our microcontroller, there's a number of different pieces that we should look at. The first is the processor. Again, we've said this already, but it is the ARM Cortex M processor. And that's what executes our software. We saw and worked through building a processor in ECE 281, so we're not going to go into a lot of the detail what's inside there, but it's very similar to what we saw during MIPS. Now, there's a lot more to this microcontroller, such as the memory, and really this system has two types of memory. It has flash ROM and RAM. So flash ROM, which is electrically erasable, and you will learn how that works in different ECE classes. It's programmable. It's read-only memory. So this looks like the spacing got a little bit messed up. That's why using OneNote's awesome. You can throw in all your stuff into a OneNote. You can have a lot more space on the sides. Highly recommend it if you print them out and try to write on it. It gets a little tight, but I try to leave as much room as possible. So this is the flash ROM. That's where instructions are stored. Opcode and machine code. RAM, on the other hand, is our random access memory. It is read-write memory. And it contains the data as it's executed. We'll talk about this later in the two buses, but we can see here there's a decode bus and an I-code bus. One of those for data and one of those are for instructions. And that allows us to really go and move information really quickly. And then we also have our system bus, which is connected to our data RAM. All right, so in regards to ports, obviously input and output ports. And the thing to note with the MSP 432 is these ports are addressable. And what that means is each one of these ports, so say like port 40, so port 4 pin 0 has its own address. And I can write to that address, or I can read from that address. Write to that address if it's in output mode, then I'll read from that address if it's input mode. So for example, the line sensor. If I want to read from it, I set it as an input, then I access that address and I load the information from that address into a register, and now I have that information that's coming from that line sensor. All right, so we talked a little bit about Harvard versus von Neumann architecture in 281, but just know that this is a Harvard architecture. That is how everything's connected, and like I said before, primarily it has separate buses for instructions or for fetching opcodes, and read-write from memory. So that just saves us time. We can get the next opcode while we're writing something to memory or reading from memory. So looking at these buses, there's actually more than just two. So the Harvard architecture just means different buses for fetching opcodes and accessing memory, but there's a lot more in the MSP432. The iCode bus is what we actually use to fetch opcodes. The system bus is where we get our data from RAM or the I/O ports. Decode bus allows us to debug, so you'll see this a lot. Allows us to access information while the processor is still working. And then the private peripherals bus. And we can see these here. These are internal to the MSP432. They just allow really quick access between the processor and these peripherals. And we'll go into what that really means a lot later, but just know there's 4 different buses, and these buses really allow for the MSP432 to work really quickly. All right, so we talked about CISC versus RISC in 281. Let's just kind of go over it a little bit more here. So ARM, the Cortex M is an ARM processor, which is a RISC processor. So that just means few instructions. The instructions have fixed length. They execute in 1 or 2 bus cycles. So in the MIPS executed in 1 bus cycle. There are some instructions in ARM that execute in 2 bus cycles. We can only load and store from memory. We don't have all these different ways to access memory. We can't access memory, and we can't read and write to the same memory location or to memory in the same instruction. And limited number of addressing modes. So those are the key characteristics. And the thing to note is ARM, while it is more advanced, and there are very advanced, the Microsoft Surface Pro are based on ARM, it is still a RISC architecture. Most instructions are 16 bits and some are 32 bits. You're not going to have to really worry about that too much. What you do need to know is just that addresses in memory are 8 bits and then the registers are 32 bits. So that's what kind of I want you to remember when you start thinking about the width of stuff with the ARM processor. Memory, 8 bits wide, registers are 32 bits, and that is why push and pop increment by 4, and we saw that last video. Alright, so it's a load and store architecture, and this is very similar to MIPS, and all that means, remember, is no one instruction can both read and write to memory. That's the same as MIPS. So we kind of talked about the registers in video 1 when we were actually applying the code and looking at it. But think of registers as just pieces of memory. Registers are located in the processor, so they're super fast. They're basically instantaneous to access them, so you don't have to go on any of the buses. But the registers allow, and simply coding allows us to store information within the actual program. And so there's 13 general purpose registers. That's storing variables, storing values, etc. And then these 3 are your special registers, your stack pointer, your link register, and your program counter. Well, these aren't special registers, but they're very unique purpose. These ones are your special registers. Stack pointer points to location on stack, just like it sounds. Link register points to your return location from a function. And program counter points to the instruction currently running, or to be processed next. These are your special registers. You don't have to worry too much about those, but these ones over here are your key registers that you need to pay attention to and that we'll use quite often. The other thing to note, so I said they are located in the processor. They're super fast, but very volatile. So through different running of the system, the registers will be erased. All right, let's talk memory mapping. So memory mapping, that's what we talked about a little bit before, 8 bits wide. This is how we map our memory, starting at 0, going up to E004, 0FFF. So even though there are multiple buses, so even though when we look at this kind of diagram up here, even though it looks like ROM, your input-output ports, RAM, internal peripherals, they look like separate units. That's just to kind of demonstrate the different buses, but they are all in the same memory space. And what that really means, and we can see that in this little diagram right here, is that we can access them through addressing, and it's all within this same memory space. So addresses are 32 bits long. So all zeros to FFFs. So address space is 2 to the 32, which equals 4 gigabytes. It's byte addressable. And that's why we have these down here where it says 8 bits wide. And so if we're storing 32 bits of memory, it's going to take 4 different bytes to store that. And so you can kind of think of that's somewhat of an issue. It works out, and that's where stuff like pushing and popping, incrementing by 4 comes in to help us. So 32-bit value exists at 4 different addresses. So, for example, 0x is 0, 0, 0, 0, 0, 0, so 0, 1, 2, 3. That is, your 8 bits wide. So this is your address. And so this whole piece of data right here, let me just do something blue. That would store a 32-bit value. And so that makes it somewhat difficult to access a full 32 bits, but it's nicely built in, and that's, like I said before, that's where the incrementing by 4 comes in, and we just need to know that when working. A lot of that's done in the background. So if I want to access a 32-bit value, it will take, if I put in the address 0x0000000, it will take all values from there, 1, 2, and 3, and store all of that into a 32-bit value. So the program counter points into ROM. And if we saw it up here, but ROM is where our instructions actually are stored. So it points into ROM, and that's where our machine code are stored. I/O devices, like I said above as well, exist in memory. So that's input/output devices. You can see your I/O ports 4, all zeros up to 5, FFFF. That's going to store every one of our input/output ports, and to access that data, we can just access that memory. So our data can be accessed using the address space. And the last thing to note, as we've already talked about, is data is stored in RAM. And to access data, we use the load words, or load, byte, load, word, whatever, and store. Byte or word or whatever we're going to store into memory. So key thing to note here is that the Cortex M is little endian, and what that means, and we can see it here, is if my data is 000F4240, it's going to load the first bits at the furthest down memory address, and then the last bits here. So little endian, basically least significant bit. Or sorry, least significant byte. Remember, byte addressable is stored first. And then so on and so forth, with the most significant byte stored last. And if you've forgotten, here is our least significant byte, and here is our most significant byte. And that's important when we go into working with the assembly code and we start programming and trying to look at where our data is being stored. You just need to know, hey, if I'm looking at that byte, that corresponds to the most significant bit. So there's a number of different addressing modes, as we see up here in regards to the RISC. It's limited, but they are there to help us store memory, store values into memory, pull information from memory into registers, and let's go over what those look like. So the first one is immediate, and these should be familiar from 281, but immediate is we're going to take and store the value straight into R0. So we're going to take the value 100, which is 0x064, and we're going to take that and move it straight into R0. So the value 100 is going to live right into that register. So that's immediate addressing. So I can store some value, I can store any value I want, 0, 1, 100, straight into a register. Indexed is a little bit different. Indexed is we're storing the contents of a register into either memory or into, contents of memory into a register. So R1 is pointing at a memory address 200004, and instead of loading 20004 into R0, we're going to actually load the value 1, 2, 3, 4, 5, 6, 7, 8 into R0. And so that's indexed. We are loading something that's at a register that's pointing at memory into another register. So you can think this, and we saw it in C, you can think of it as the contents of R1. And so really it's the contents of the memory address, so the contents of the memory address R1 is pointing at. So in this example, R1 is a pointer to memory address 200004, and then we take the contents of that and toss that into R0. And with index as well, we can do offsets. So we can offset it. So R1 is pointing to 20004. We offset it with a value of 4. That's going to go down to 8. And we're then going to take that value and store it into R0. So that is indexed addressing. So you can think of address index as using a pointer, and we're going to be pointing at different values or memory addresses, and we're going to be getting the contents of those into our register. And that's typically what we're going to be using load and store for. All right, PC relative addressing is basically the same as indexed addressing. Instead of using a value, so in indexed addressing, we're using an offset of a value in a register. In PC relative, we're using indexed addressing using the PC which is the program counter, as the pointer. So the PC always points, like we saw before, points to the next instruction to run. And then PC relative will then look at an offset based off where we are in the current program. So let's take a look at this example where we have a variable count, a pointer to that variable, count address, and then we want to use those to access this variable count. So count adder is going to be basically what our address is, and that's going to be storing the variable count. So when we look at the code here, we see there's two load instructions. So that first load instruction, so let's actually, before we get there, let's take a look at what these variables and constants are doing. So variables and constants in, let's just go down here. So variables and constants in assembly are stored using PC relative. Stored and accessed using PC relative addressing. Okay, so let's say we have the variable count, and that variable count is a label. So think of it, I mean, variable, label, same thing, defining a 32-bit variable in data space, or also known as RAM, right? And it's located at 0x2000. So this is the memory location of count. And so to store that memory location 2000.0000, so we can access count, that's where we start using PC relative, and that's where count adder comes in. So when we use this .field pre-directive, what the assembler does is it stores count adder. So now count adder is a 32-bit constant with value of that address pointing at count. And what it does is the assembler places the constant in ROM, so in our code space, relative to the program counter. Okay, so count adder, that actual value, represents the PC relative location of the constant 0x20.0000. So if we look at the actual commands here, so we have two loads, 1 and 2. So let's look at those first loads. So looking at the first one, the first load, oops, it loads count adder, which when we say count adder, what we're really saying, so count adder here is the same as PC plus 8. And what happens is when we store this constant into ROM, the 2000.000, when we store that into ROM, we store that each instance of count adder is not going to be always PC plus 8, but this instance is going to be PC plus 8. If there was a different one, say further down, it might be PC plus 1. And that is all done at assembly. So every time we see count adder, it looks at, okay, how far from this instruction is that variable, or sorry, is that constant stored? And it knows, as the assembler, that we're going to be PC relative. And so when we plug in, try to load into R1 the count adder, what we're really doing is we're going PC plus 8 down there and stored in memory is going to be 0x200. So what happens is R0 equals 0x200, 000. And the thing to note is it got this value to this constant using PC relative addressing. And that allows us to be very dynamic, because count adder won't, potentially when the code is created, it won't necessarily be in the same spot every time. So we use PC relative, which is indexed addressing using PC as a pointer, and then PC points to the next instruction to run. Don't forget, that's where the program counter is currently pointing, and then all of these count adders are based off that. All right, so the first load takes 0x200, sets it equal R1, sorry, not R0. And then the second one now takes the contents of that, which is equal to that count variable. So now R0 equals count, or whatever that variable is. And that's the basics of PC relative indexing.